Hi, everyone, and welcome to this new episode of Additive Talks, our series of panels that focuses on discussing the use of additive manufacturing technologies in a given industry. While today's session is quite unique, we are going to focus on lean product design strategies in manufacturing. This means that examples and insight that will be shared today can come from a wide range of vertical industries, including aerospace, automotive, medical, space, architectures, etc. Our goal today is really to provide the right tools and tips to address some of the concerns and challenges, raised when we look at the design methods that have somehow emerged as essential companions to additive manufacturing. For those of you who do not know me, my name is Katie Sinze, managing editor at 3D Adapt Media. And I have the pleasure to moderate this panel alongside two wonderful experts. So I'm going to ask them to introduce themselves. Josephine, can you please introduce yourself as well as the company you work for?
Sure. Hi, everyone. Thanks for being here and listening in. My name is Josephine. I am the strategic engineering lead for a company called Hyperganic. We used to be a startup. We've been growing ever since. And we use computer code to generate physical objects. So we try to come up with a completely different way of how objects are built in the future, not through manual CAD drawing, but through computer code. So I hope to explain a little bit more about that. Regarding my background, I'm an aerospace engineer by training. So I will talk about some stuff that I did with rocketry, but all sorts of interesting engineering stuff that comes to the AIM space I'm dealing with at my daily work.
Oh, interesting. Thank you, Josephine. We are really happy to have you there today. What about you, Erin? Tell us more about you, what you do, and the company you're working for.
Sure. Hello, everyone. I'm Erin Comey, and I am an additive manufacturing specialist at Etteplan, which is an engineering services company that has around 3,900 people working in Finland, Sweden, Central Europe, China. We even have a couple of offices in the US as well. And basically, my role as an AM specialist is that I'm focusing on simulation-driven design for, in particular, metal additive manufactured parts. And I'm sitting on the additive manufacturing and optimization team here at Etteplan. And we have our team members are located throughout Scandinavia, but basically we're working on customer projects trying to sort of lift the profile of additive manufacturing in a large number of industries. And so we're doing that through simulation, design, trainings, and this sort of thing.
Thank you, Erin. So for those of you who are listening, to Additive Talks for the first time, please note that you have a Q&A chat in front of you. You can always write any questions, any remarks, any insights that come to your mind, and then we'll be reading, those questions, those remarks, or those insights at some point along our conversations. And yes, and also, our panelists are also here to respond to any questions that you have, even if they are not directly, linked to the original topic. So that's it. So yeah, let's move forward to our conversation. So it's really hard to recall, ladies, that there was a time when, we only talk about design for manufacturing. The concept of design for additive manufacturing has emerged so fast that it seems to be on everybody's lips. So just to give a sort of context or, background to this conversation, let's go through the different design strategies, that engineers can explore in their, product development process. Erin, do you want to start, by giving some of the, design strategies that we can explore? That engineers can explore in their day-to-day job?
Yeah, of course. I think that first and foremost, in every project that comes to our desk, we really want to take a close look at, what are the needs of the customer, what are the needs of the end product, and based on that, we assemble a team and think of the tools that are needed to sort of solve this given problem. And so, when it comes to sort of like these design methods or strategies, we tend to use simulation to drive our design wherever possible. And so that might include tools such as finite element analyses, so structural analyses. We might be using computational fluid dynamics. We use print process simulation, for example, when we're talking about, laser powder bed fusion, or maybe sintering simulation, when we're dealing with metal binder jetting. But then at the same time, we have usually we have these conflicting, design objectives. So we want to make, a functional, high-performing component as cheap as possible, as quickly as possible. And so in order to sort of deal with this multi-objective, essentially optimization problem, we might look at tools such as topology optimization and generative design. So especially in those cases where you want to minimize material usage, minimize the mass. So for example, in aerospace industry, obviously there can be huge cost savings, with every kilogram saved. So in those cases, we're selecting the tool depending on, the product that we're trying to design.
All right, I see. Josephine, I feel that you have a different background, a different, opinion on that.
Yeah, I come from the practical side, so I'm an engineer who later on came onto additive manufacturing.
Okay.
The way I work in my everyday life is actually a little bit the other way around. So usually, or what Erin just explained, is you have a design and then you do a simulation afterwards in order to improve on the design in case it doesn't comply with the overhang angles or the whatever you want to take into account for additive manufacturing. When I design an object, I don't draw it by hand on a computer screen. I actually write computer code and then execute my program, and then the geometry is automatically generated through that computer code. And that actually enables me to turn my workflow around. So I can take some of these constraints into account so that they are taken into consideration as my geometry grows, which means that afterwards I don't necessarily need to check for overhangs. I can right from the start tell my computer program to never design anything that exceeds an overhang angle of, I don't know, 45 degrees, 60 degrees, whatever I want to input. And then the visual output is sometimes surprising. So if I change the limiting overhang angle, the entire geometry will be more stretched, for example, or will be less stretched because it's inherent in the rules that I use to design the object. So this is a different approach that we are taking. If you like, I can show you an example. I brought some 3D printed objects with me. So I worked on a rocket engine. I don't know. Yeah, you can see it like this. So this is an early prototype. Don't take that too literal, but it's an aerospike rocket engine. I can show you the metal printed one in a second. But when you look from the side, it has these manifolds here.
Okay.
I'm slightly sorry. And here, the manifold is vertical. So the shape of the manifold is automatically chosen by a computer program. And in that case, it's kind of rhombical or hexagonal because I can print it in that orientation. When it curves up, it goes automatically to a round shape because that's optimal for fluids and I can print it in that orientation. But as soon as I go horizontal here, it switches back or it smoothly transitions back to a sharp shape. So this is something that you wouldn't draw manually in a CAD program, but for me, it's just one function in my code. So to answer the question, I can take a lot of assumptions when I design the object rather than then afterwards going back and trying to improve on it.
All right.
Can I add a comment there?
Okay,
I totally agree. And I think that when we have seen the greatest benefit gained when designing for additive manufacturing are those cases where instead of looking at an existing design and designing around an existing assembly, we actually take a look at, okay, what are the functions that this part needs to perform? Think nothing about the space and only look at, what does this part need to do? And if you can ignore all of the other perhaps surrounding components or the influence of everything around that and focus just on, what are the functions that this needs to perform, I think that's when you get the most unique solutions and you can really see like the great benefit from these like the design freedoms that we get with additive manufacturing.
Okay.
Yeah.
Please, Josephine, go ahead. Sorry.
Maybe to add to that, in the broader scheme of things, what we see is that engineering is moving away from a visual paradigm where people have something in their head and they just draw it. We move to a functional paradigm where engineers work on a more abstract level and they define, okay, I have this component, it has this function, it has this constraint, and this is how I want to optimize it. But people don't think of the geometry per se. The geometry is kind of a surprising result, or not so surprising, depending on what you do, from the limitations, constraints, and construction rules that you define. And I think this is very interesting from an engineering perspective, because when you deal with a visual paradigm, you're basically limited to what you can imagine in your head. So what you draw is basically limited by the complexity that fits in your head and the amount of time that you have to draw it. If you automate the drawing process, we can actually reach higher levels of complexity that goes well with additive manufacturing and moves engineers to a more abstract level, which is very powerful.
Okay. Yes, and you don't have to have the best sort of CAD designer on the planet to come, reproduce these ideas when it's sort of integrated in the system.
Yeah, correct.
I just want you to, to keep those initial remarks, because I feel like, we are going to deep dive, into specific details of each of the key responses that you just gave, throughout the conversation. Right now, I would like us, to focus a little bit on really two design strategies that are, actually becoming more popular than others. And these are generative design and topology optimization. And it's really weird because, as the generative design process takes off in many organizations, certain CAD vendors, have begun rebranding and selling, topology optimization as generative design. So it's really weird. And I would like to know why do we have some sort of confusion between these two concepts? So, Erin, can you provide us?
Yeah, of course. I think the confusion comes because quite often the objective is the same in both, that you want to optimize the use of material in one way or another. And that is usually meaning that, all excess material has gone away. And so I think that as the term generative design has become trendy, some of these software companies have unfortunately, applied it to the tools that they have. But that's not to say that they're not. Some of these CAD companies actually are using generative design, and others are using topology optimization, and that's not to say that some aren't using both or offering solutions in both. But do you want me to jump back and try to define these a little bit?
I'd like to know first if Josephine has another point of view on that, or if she feels the same. Do you agree with what Erin just said?
So if you want to hear my opinion, I would say that both terms are very fashionable for people to use. And I think it's overused, frankly, because just because we have the tools for do a certain type of topology optimization, or there are a couple of plugins out there that allow you to do certain optimization steps with generative design, everyone uses it, but it's not always the method that you want to use it. Just because the tool exists, everyone jumps on it. Exactly. And just because there are latticing tools out there, everyone puts a lattice into everything. So sometimes I have this gripe about that people, like, it's very fashionable and everything starts to look like a bone because everyone is topology optimization. So it's just one method, and I would like to see that a little bit more diversified, in a sense that people actually reflect, what is the method I want to use? Does it have to be that tool, or are there other ways of light weighing something, smarter ways that are more tailored towards my application?
Exactly.
So, yeah.
Exactly.
Yeah.
Right. But if you had to define each of these methods, what would you say? Erin, you wanted to go ahead with that.
Well, I can, if that helps. But I think that when you start with, if we're talking about FEM-based topology optimization, basically the starting point always is that you need to create your design space, and you need to identify your loads and boundary conditions. And so when you're doing this, well, jumping forward, and the whole point of topology optimization is to, create a structure that can withstand the forces that you are applying to it, and generally you're trying to, at the same time, minimize the mass or maximize the stiffness of the part.
Okay.
And I think that with this approach, and because it's based on finite element method, there's quite a lot of restrictions to what you can do and to sort of how rough the final output is of the design that you're getting. And then when it comes to generative design, this is AI-based, let's say, design exploration process, and it's usually utilized to generate, potentially hundreds of potential product designs.
Okay.
And each of those design iterations is sort of learning from what is good and bad about the previous designs. And so again, you need to be able to define some sort of, system of loads and boundary conditions or some other constraints that the tool is utilizing, but it's not necessarily so restrictive as topology optimization. And the other thing is, when you do generative design, you don't start by identifying a design space. So all space, your design can exist everywhere except where you put limitations. So if you say that I don't want material here, that might be one of your constraints. But you're not limited to a fixed geometry at the beginning.
Okay.
Yeah, I would frame the term generative design a little bit broader. I would just generally say it's when you start automating certain aspects of CAD.
Okay.
And most of the generative design methods are based on traditional CAD kernels. And if you want to automate processes, you need a geometry representation that doesn't fail. Otherwise, if you automate it and it fails after the second iteration or the 100th, well, then, yeah, it's not really automated. So then you know that from CAD that you have sometimes when you want to do a Boolean intersection or a union, it fails. And then you move some part like a fraction of a millimeter and suddenly it works again. So this is not well tailored towards automation. And that is the problem that I see with lots of existing generative design tools. If you want to automate, you need a stable basis. So we at Hyperganic actually use a different geometry model to represent geometry that makes it more stable towards automation. So that's generally, if you want to do generative design, it needs to be automatable. What Erin alluded to is that you can then build feedback loops. So both what you defined as topology optimization and generative design is the ability to create decision trees or feedback loops in order to have the program come up with a solution.
Okay.
And I don't know if we want to talk about topology optimization in more detail.
I just have one question because you were talking about Hyperganic when you try to explain how generative design works, and I wanted to know if Hyperganic software is a type of generative design tool or not at all, or is it a different tool? Because it's a little bit confusing. I'm sorry.
Yeah, good question. So we try not to use generative design as a term because we think we go actually one step further. I alluded to the fact that you have to change your entire geometry kernel if you really want to do computer generated design. So the method that Hyperganic proposes is called algorithmic engineering. And it's kind of generative design taken to the next step where it's actually feasible and not shoehorned into old existing CAD ways of doing things. We want to use a blank sheet, a different way of geometry generation, and build algorithms on top of it. So it's kind of the next evolution of generative design, if I were to define it.
Okay, I see. On the third. Erin, you wanted to add something? No?
Well, I was curious if you are familiar with N topology and the way that geometry is defined in that tool, and if you are willing to sort of compare the similarities or differences between these two tools, because I think both are reasonably new and very interesting for this space.
Yeah, so what I have to give credit to Topology is that they actually pioneered a new method of geometry representation. So traditional CAD kernels work on surfaces because they are used for, in the past, they were used for milling processes, traditional manufacturing processes, where you start with a block and you just move material away until you hit the surface. So you're interested in the surface. Makes sense for that kind of paradigm.
Okay.
Topology were the first ones, or I don't know the first ones, but they commercialized on a different way of representing the geometry, which is an implicit modeling method, where you define every geometry through what basically mathematical functions in space. And this is very smart if you want to do stuff like latticing or mathematical patterns that repeat itself. It's very efficient for that. But again, if I maybe show you the project that I've been working on,
Okay.
let's look at the picture for a second. So this is a rocket engine that I developed. We showcased it in the US 2 months ago. And I tried to model that in an implicit way. So this is still generated through computer algorithms, basically mathematics. But the way that uses the geometry representation, you cannot really go to much more complex stuff. So you wouldn't be able to define a rocket engine like this purely from implicit modeling.
Mm-hmm.
So Hyperganic takes a more basic approach, actually. We use a very simple representation that we call voxels. So we have the build volume of our printer and we divide it into tiny little cubes, a lot of cubes. So you want to optimize that for your computer in order to make it run fast. But then we actually just say, okay, this voxel is material, this voxel is not material. So we basically paint pictures in space and say, here's matter, there's no matter, and so on. And there are lots of grayscales in between. But this method can never fail because it's not surfaces, it's kind of volumetric modeling. So I can just paint over a voxel if I want more material there or less material there. It's almost like drawing a picture out of pixels just in 3D. So I can go with a brush in paint and just draw a couple more white pixels, and then I have added some matter. And this is kind of how we represent our geometry. And this will never fail. So it can come up with stupid results if I do my job wrong, but it will always be a geometry that I can actually print in the end. And as we found out, you can drive the complexity of objects much more because it's more reliable at its core.
I have some questions about that. I was wondering, how does the voxel size that you're using tie into reality? Is it somehow, you said the outer size is the dimension of your build volume, but are the individual voxel sizes somehow linked to powder particle like size,
Yes.
or layer thickness, or laser beam diameter, or like
Yeah.
these physical dimensions, or
Yeah.
or how does that match?
So you're getting close to the idea. The original idea was to come up with a geometry representation that is tailored towards 3D printing. And every 3D printing process has a resolution. And
Okay.
the idea back then was to have a model where you can basically model each pixel or bit of matter that the 3D printer can output. So yes, there is a certain resolution to the print process that is then reflected in my voxel size. If I want to be right on the edge of what the printer can do, if I just want to model a very basic geometry, then I can actually lower the resolution, and that will ramp up, well, that will speed up my algorithm to execute. So what I take into consideration is basically the print process, and then what is the smallest detail of my design versus the overall size. And that gives me a handle to control how long the execution process will take and what kind of details I can actually resolve in the geometry.
Okay, and then if you don't mind, I have
No,
one
Erin,
more
come on.
question.
Come on.
So
I will remind
like with
the audience what I wanted to say later. Go ahead with your question.
yeah, well, when it comes to these extremely complex designs, one of the biggest issues has always been, going from either our CAD tool or, something like Topology or whatever, and moving it from, what we see on the screen to the print, the preprocessor. And, you know, we've been dealing with these SDL files for ages, and they're a nightmare when you have like highly detailed part, you know, like this one. And so I can see that obviously there must be a direct connection between like the output from Hyperganic and you know, the printer itself. And so I imagine that your collaboration with EOS has something to do with this. But could you say something about that, like the transition from, you know, the design you see on the screen and how you pass that information to the printer? Because I mean, of course, especially with, you know, these high performance parts, you really need to take into consideration, you know, the different print process parameters that you're using. And, you know, and so if what you're, you know, like the approach is changing with every different design, I was also wondering about, you know, how you deal with like quality assurance and those sort of things down the road.
Oh my gosh, you're asking my
sorry.
Okay, Josephine.
Sure. So you're touching on all the right points. So I can tell you. So I can tell you the theory and then the practice of how this part that you see on screen come alive.
Okay.
So in theory, we have interfaces to different print methods. So we can export image stacks for resin printers. We can export G-code for FDM printers. We can export CLI slices, for example, for metal powder bed fusion processes. And the problem that we had with this Aerospike engine is that it was so complex. It was, in fact, the most complex part that AMCM and EOS ever printed. So I wanted to send them a couple of kilobytes of slices, which would have been super efficient. They could go directly onto the printer. The only thing that they didn't trust me on is that I took all the print constraints into consideration. So they said, we need to check that it's actually printable. So they wanted an STL. So I'm like, okay, fine, I give you an STL, but it turned out to be like 6 gigabytes for the ones that you see on screen, dialed down. So it was a massive pain, and it basically broke most of their workflows. They had like a computer that could deal with the file size. So that's a big problem, and this is why we drill so much on, okay, and this is actually why we're doing this collaboration. EOS now tells us exactly what their constraints are, so I can encode them, and then they can trust me that when they put the slices on, it will print. And the stuff that I sent them already printed in the first go, which was a great validation for the stuff we do. But of course, I over-designed a lot of things that you see on screen. So for example, you would take a constant overhang or a constant wall thickness as the limit. But the truth is that some of the printer manufacturers, they actually have curves. So they know if the overhang gets shallower, the wall thickness needs to be thicker. If it prints upright, they can actually print thinner. So we are now at the process of encoding these kind of functional dependencies. And then you can go even further in terms of being right on the edge of what the printer can output. So I hope this was the last time that I need to deal with like huge gigabytes of SDL. Yes, it's a pain. I completely
quick random questions about that. How long did you take, to design this part?
Oh yeah. So that's an interesting question. So when I design the algorithm, obviously that takes some time because I try to encode everything I know about rocketry into that process. So I try to come up with the rocket equations, isentropic flow conditions, and so on. So I can link my physical requirements to the shape that is generated. This took a couple of months to encode all of that. But the benefit of going through that pain is that you then have an algorithm that you can feed with all sorts of requirements, constraints, and it will repeat the process much, much quicker. So if I not want to do one design, but want to iterate across 100 or I don't know how many, it's actually much quicker. So the Inconel printed one that you see on the screen, the silver one, is about 40 centimeters high. And that took about 10 minutes to generate. The big one, printed in copper, that one is 80 centimeters high. That takes more than half an hour to generate. So yeah, obviously it takes longer with the complexity level and the size. But still try to imagine that to design manually. And then again, if you want to tweak a parameter and again, you will not be able to like do that in an hour. So The method that we apply has a high initial hurdle because you have to write computer code. But once you have that algorithmic model, you can just reuse it and rerun it. And it's much, much bigger. So the method starts to scale once you want to iterate a lot. And that's interesting because if we get into this high performance industries, you never hit the optimum with just one go. You have to iterate, you have to trial things, you have to print, you have to simulate, and so on. So this is where it becomes very important.
I guess I have another question about the complexity that has been introduced here. And obviously, if you're using generative design, one of the, you need to have feedback from each design to see how you're doing compared to, the initially set objectives or criteria that you have. And so if you have such a complex design, how do you get that feedback through, like CFD or FEM or, other simulations, or are you somehow avoiding that totally? Because I would not want to create a FEM mesh or a CFD mesh of the air volume here, either, because those are also really complex.
Yeah, that's right. So to get to this prototype print, I didn't actually simulate it because I wasn't able to simulate it. You're touching on another point. I tried to simulate that with SimScale, a market leader in online simulation, supply, whatever. They can't deal with the complexity either. But two ways to solve that. So the first way that we actively engaged on is we acquired a simulation company that works directly on the voxel level. So what usually is the pain point is the meshing. So you have an outer surface and then you want to figure out the volumetric mesh. That's the pain. If we have a simulation that runs on the voxel model, we speed up the process completely. And we had a company that simulated it within 15 minutes. It's not validated yet, but it worked at least. And we acquired them. So they're currently including that into Hyperganic. The second approach is because you use algorithms, you have all the knowledge about the system in one place. So the geometry is just one output. Other outputs is that I actually know everything about the combustion chambers because they are classes, they have attributes much more than just the shape. So I could actually generate from that shape automatically a simplified version that only takes the inside of the combustion chamber into account, and meshing that would actually be okay. So you can kind of split up your geometry into logical compartments and simplify where you want to, and then kind of have parallel streams of where you want to engage and feedback in your system. And the final geometry is kind of how these threads all come back together. So it gives you a lot of freedom beyond just dealing with the geometry that you output in the end.
Okay. We have one question in the Q&A chat about this topic. I would like us to answer this before we move to another point of the conversation, if you don't mind. So the question is from Fadil Kayori. I'm sorry if I pronounce your name very badly. So has the aerospec engine been tested yet?
So this one has not been tested yet. We just showcased it like a month ago. But through showcasing it, we got a lot of interest from the space industry.
Okay.
So we are currently engaging with a couple of entities and trying to figure out whether we get support to actually test it, which would be awesome. But we are a software company, so we will not test that stuff on our own. But in my dream, yes, we partner up with a space entity or a company, and we actually test it. Because if you have a validated algorithmic model that works, that's kind of a tipping point, because then you can give that algorithm to people who want to develop in the space, and they can use that as a starting point and develop on top of that, because we open source the code for that one. So everyone can look at how I build it and can improve on it. But the baseline is hopefully in the future being validated and tested so that it works. And that would be very interesting. One last sentence on aerospikes in general. They have never flown successfully. So they have been conceptualized back in the 60s. They promise a inherent performance gain up to 15%, which is huge.
Okay.
Actually, neither NASA nor the Japanese nor all the space entities managed to successfully build and fly one, because they're very complex. And they couldn't manage it with like traditional engineering and traditional manufacturing. But now the hypothesis is we have algorithmic engineering and we have 3D printing. this should be the two tools that allow us to make aerospike technology actually possible. So it's quite a fashionable topic in the space industry, if you like.
Okay, thanks, Josephine.
Yeah, I started that now, so we can move on to other topics.
Thank you. We still have 30 minutes before the end of the panel. So if you have any questions, please, this is your chance to ask Erin and Josephine any questions regarding DfAM. Yes, or anything else regarding this topic. So Erin, Josephine, I often hear that when designing for AM, one should be able to take into account a human element. What's that? What does it refer to, Erin?
Yeah, well, I think that I see it that you could take that two ways. I think when we are talking about simulation-driven design and these different design tools that we might be using, I think that this can include the influence of the person that is sort of creating the algorithms that are making the aerospike engine, or how the engineer is interpreting the results of a topology optimization to create a final design. Otherwise, like when I hear about the human element of design, it can also be about the end user and how we design to sort of meet the needs and the limitations or requirements of the person that's using the product at the end. So I guess depending on how you're looking at that, I think you can approach it two different ways. So do you want to specify one of those and discuss further, or?
No, not really. No, not now.
Okay.
But Josephine, do you agree with that? Is it really like sometimes just the designer, I mean, the engineer that designs the part, or sometimes the end user that we have to take into account?
So I was originally thinking about the first aspect that Erin mentioned. When we talk about automating engineering processes, and then most engineers or many engineers think we want to replace them, which is not true. We want to have these new software methods to enhance their capabilities and move them away from manual workers to actually people who are supercharged in terms of their productivity. So I think it's very important that there is a human element to how we use computer algorithms. Like, machines and humans need to work together. If you only decide a machine to do everything, it will be crap. If you only use a human, it will be limited by whatever he can do. So I think we need to stress that these two things need to come together, and everything that we automate through computer algorithms will not harm the engineer as a human. It will enable him to do new things.
Okay, great. There's also something, I'm sorry, I'll need to come back to that, because Erin mentioned that earlier at the beginning of our conversation, that materials, are a key element that we need to take into account when we design, a specific part for product, in a product development process. So could you describe how we can take materials and then the manufacturing process as well as key elements into account in a specific example?
Me or Josephine, do you want to take this one?
And I was talking to you, Erin.
Oh, sorry.
Because you mentioned, the importance of CO. So I wanted to know if you have like specific examples that you can share. Or
I would have one.
I guess I could say one quick case in electronics industry. Unfortunately, I can't show anything, but I can tell a little bit about. I think when using these design optimization approach, we were redesigning an extremely small but highly weight critical component that was originally made with injection molding. And what we found was that by using topology optimization and really optimizing the design, we were able to go from this injection molded part, which had some difficulties with manufacturing, to a titanium part that is created with metal binder jetting. And even though we went from plastic to metal, you would assume that it would suddenly weigh more, but actually with the topology optimization, we were able to produce a part that, you know, could bear all of the loads and actually weighed considerably less and was easier to manufacture in the end.
Okay, interesting. Josephine, you wanted to share an example?
Yeah, I wanted to add that there are a lot of interesting print processes now coming to the market that can actually combine different materials.
Okay.
And as I explained, we model geometry through little voxels, so little volumetric elements, which means that for each voxel in space, I can attach what's the material, what's the density, or whatever. So I can attach data to each point in space. That allows me to have material transitions within my design. So, for example, the arrow spike I would overlay with a distribution where I assumed whenever I'm close to the wall, I want a stiffer print process, abstractly speaking. And whenever I'm further away, I want it to be more porous in order to optimize for lightweight, for example. I have another example. So I designed a lung bubble. So that's just a model of it.
Okay.
Of our resin printers. It kind of looks very organic. And there are a couple of multi-material printers on the market that can print soft tissues with different stiffnesses and so on. So I actually designed that lung bubble a little bit smaller, where I encoded into the different parts of the object the material that it should be printed in later. So, for example, the outer capillary tubes here, they were a little bit stiffer than the base shape that was softer, or the other way around. And you can model transitions of the material in between, especially in bioprinting, but also in the metal space that enables completely new ways of utilizing materials, because traditionally you have a block of aluminium and you mill it away and it will forever be aluminium. With these kind of mixing methods, you can, in the future, I think they're not quite ready, but some of them will get close. You can get materials as you go, and that creates completely new materials that we haven't seen before. And it's an interesting field for the material scientists. But if you learn about how these materials behave as you mix them and so on, you can start including that into your designs, and then you can smoothly transition from a stiff material to a soft one, and then you don't actually need a joint because you have a compliant soft part in the middle and so on.
Yeah.
It enables a lot of new ideas for product design that traditionally you would have part one, part two, and you bind them together. But if you can transition, well, you might come up with a completely different way of doing things.
Okay. Let's and then do you want to share something? Because I wanted us to, respond to the questions. But if you have any questions or any comment, go ahead.
I was just going to say that it doesn't actually need to be two different materials either.
Okay.
So in metals, they're also working with adjusting the print process parameters in order to sort of achieve these basically different effective materials by changing, for example, like the porosity that you have. So introducing porosity, whereas usually, you want to eliminate it totally, you might gain some benefit in terms of, how it behaves if you introduce it. Or, I mean, it's also being done with design as well. So with optimized lattice structures. I know that you're trying to get away from those, but basically, changing the thickness of really tiny structures throughout, you can basically change the effective stiffness throughout in the same way that changing the material might, or in a similar way. And I think these kind of things, they can be interesting in terms of how the material reacts, but then there can also be additional benefits in terms of like added functions like filtration, or these other properties that you might need or want in the design. So I think being able to design in the way Josephine has been explaining, and create this type of voxel output that gives you this freedom, allows you to really sort of explore these like new ways of creating designs that you get the effective change in your material behavior that doesn't require two different materials to mix in your printer.
Yeah, so generally speaking, additive manufacturing gives you kind of a fourth dimension to design in. Before you were kind of dealing with the three-dimensional shape and that's it. Now you have a fourth dimension, like how do you want to distribute the material inside your shape? So it's quite cool.
Yeah.
That's right. Ladies, let's pause for a minute because we have 15 minutes less, and I really want us, to answer the questions from the audience. And we have 3 of them in the Q&A chat. The first
Okay.
one, the other one is from Enrico Berger, who is asking if there is any software solution that can provide costing insights. So what can you say about that?
I think that yes, and it depends on what manufacturing process you're considering. Quite often, the solutions aren't linked directly to your CAD or your optimized design. Very often, it requires that you actually have a design ready and that you upload it. And actually, in Etteplan, we have found that this is a huge issue because it's hard to sell the cost benefits of additive manufacturing if you can't predict what the final price will be before you have the design. And so we actually created a tool for laser powder bed fusion, which will give a pretty good price indication if you know something about the basic dimensions of your final part. So you don't actually need a CAD or a drawing, but if you know something about, or if you can predict approximate volume and the size and materials that you're using and that sort of thing, we're able to predict in advance what the cost will be. I can write in the chat the website where you can go and find that tool. It's free for everybody.
Yes, please.
You just
share it please on the chat, on the Q&A chat. Josephine, you wanted to add something regarding this?
I think it's generally hard to predict the cost in a generic way, such that it works for everything. I think it's very project dependent. For example, I can give an example. We are working on an air conditioning project where we design all of the components of the air conditioning unit, and we try to make the overall assembly as cheap as possible. So we don't actually focus on the individual part, but we look at the entire assembly. And it's quite interesting what you can do if you take that into assumption, because I had a discussion with one of my engineers, and he said, oh, it would be very smart to include like a turbine into the air conditioning unit to recover the pressure. And he said, okay, but that's nuts because it adds an additional complex part and it makes it much more expensive.
Yeah.
I said, well, not necessarily. As long as you can fit all your components in the same build volume, it's roughly the same price.
Okay.
So it opens up some interesting thoughts of actually looking at the 10 components that you have, try to fit them into the same amount of parts. So you might actually want to go for a design that is not optimal, but it's more rectangular, so you can stack it with the other one, or this fits inside the other one, so you can print them together, so this kind of three-dimensional puzzle. And I do think there are some interesting opportunities to kind of make this nesting that we currently use more elaborate, that it knows more about the different components and not just stacking the same component one after another. But yeah, cost is hard, I guess, to generically predict before you actually know how it looks and what you want to use for materials and so on. And also, cost should never be the prime objective, because if that's the only objective, you better off not doing anything because that's the cheapest, right? So there's always like the performance should somehow be the first objective, and then price should be the second one.
I don't know that I agree with that, because we definitely have had cases where, there were other objectives. We were able to move manufacturing locally and that sort of thing, but cost is king. Like at the end of the day, if it costs too much, you can't justify it. So of course, if you can improve functionality or performance, that definitely has a value, but it's always a harder sell if it costs 5 times as much as something that they have that works now.
Yeah, I understand that this was a bit controversial. I mean,
also, if you keep in mind that it's easy when you're the provider to say that cost is not really important, that you don't have to focus on cost, because when you're the client, the manufacturer or the OEM that should be receiving the part that you're going to produce, cost is definitely important in this side of the line. You see?
Yeah, sure. I just think with 3D printing, we need to be at this stage still be careful of what use cases we actually engage on, because for certain applications, it makes total commercial sense already, because you cannot achieve the functionality any other way. But sometimes people, again, try to shoehorn something into something that is not ready yet. So yeah, there are applications where people want cost competitive for a not much more performant part and want to 3D print it. Maybe not the right application yet. I do think it will change. And I do think that people don't take the entire chain of cost into account. So sometimes you have to ship parts around the world in order to actually build something. If you can eliminate the entire supply chain through 3D printing, and the 3D printing part itself is more expensive, but over the entire production chain, some applications also make sense, but people focus on just the one part and not all the rest that they eliminate. So it's very much a question of perspective.
Okay.
I think it's true, but I think that it's not only a tool for the aerospace industry. I think that we can't look at the sort of obvious wins all the time, and I think AM has a home, across pretty much all possible industrial verticals, and I think it's about finding somebody who understands basically this work with the customer or the product owner, linking them to somebody who really understands the AM processes and how to get from idea to design for AM to manufacturing, production, quality control, all basically the whole workflow. And so I think it's about pairing the right experts in the right way.
Okay. Let's try to answer the next question from Yan. So will the generative design work with any CAD data, both as CAD data input and the CAD data output?
So I can answer from our side. No, not necessarily, because I explained the limitations of the CAD data model in the past. It's prone to failure if you try to automate it, and it gets a bit nasty if you drive the complexity of objects.
Okay.
So I can give you an example. That's my last printed part that I have. This one here. So if you present such a structure through surface, it's actually a very large file, because this thing has a lot of surface. If you represent this object through its volume, like we do with voxels, it actually doesn't have too much volume. So it's not too much of a complex part in that sense. So we as Hyperganic are only compliant in certain aspects with the existing CAD data. And that's not because we're ignorant, that's because we see it as a problem in order to achieve our goals. So I think not everything works well with the existing data models there.
But that's not to say that there aren't generative design tools that work really well with existing CAD tools. So I think it depends. If you're not requiring these highly complex parts like the aerospike engine or that piece that Josephine just was showing, but maybe more, I don't know, traditional, like organic shapes that you get from the standard generative design or topology optimization, then I think you can easily work with existing CAD tools in that sense. And I would say that I also have experience playing around with some generative design tools from different providers and also the topology optimization. And I think that it's definitely getting easier and more straightforward to get that CAD data output from the more standard or simple optimized designs than it used to be. So I think in that sense, the workflow is becoming a lot more efficient than it was, say, even a couple of years ago.
Okay, interesting. The last question that has just been written is the one from Peter Runner. In cases where you are trying to minimize compliance, how do you specify the stat design geometry domain in generative design?
I think if you're using this more traditional, like CAD-based generative design, you don't start by specifying a design space. You can specify where where you must have material. For example, on load-bearing surfaces, you need to include those so that you can actually apply the load to something. And then I think generally you can specify regions where material doesn't exist. And
Okay.
then, yeah, and then basically all other space is fair game.
Okay. Erin,
Oh,
do you have another point of view?
oh, you mean Josephine?
Oh, Josephine, sorry. Sorry.
Yeah, so the design space is determined through the print process that you want to use, in our case, most of the time. So the first kind of toggle in my application is what is the printer that I want to use, and that determines my space that I have available. That's kind of the workflow. So for the aerospike in my user interface, the first thing is drop-down menu. Do I want to print it on an M290, M400, AMCM machine, whatever printer I want to use? And then that propagates through all my algorithms that are based on height and width and whatever. They are informed by what is the print volume. So I'm not talking about topology optimization here necessarily, but resolution and print volume is kind of the very first input. And then this gives us the playground to then execute the rules of how geometry is created. But all of them are informed by what space is available to start off with.
Okay.
I have a question about that. So I think the optimization in topology optimization is a little bit misleading, because where there's almost never a problem where there's one true optimum, because there's conflicting design objectives that are at play. And so I guess now I just totally lost my flow here. I'm sorry.
No problem. Maybe you will come back.
Yeah, please let me come back.
Maybe one note, since you mentioned topology optimization again, I would say that also the common perception is that it's only limited to structural optimization, which is not necessarily true. As we said before, it's basically building feedback loops, and what kind of geometry and what kind of reaction you implement can be totally different. So for example, we work on a topology optimized electric motor design, where we have these kind of copper coils that are wound for an electric motor. And then the topology optimization actually pulls and pushes the geometry around, so it doesn't remove material. It's a completely different way of handling the simulation result, but it's still a feedback loop. And we also call that topology optimization. So I think this method has credit in many more fields than just the structural light wiring. This is where it started off. But from the methodology, you can transplant that onto different industries, different simulation techniques, analyzation methods, and so on.
I remember my question now. What I was getting at was that, so usually when running topology optimization, you end up setting up the problem in a number of different ways to sort of force the design in one way or another. And I was thinking that if you start all of your generative design cases by limiting the design space, do you find that you sort of miss some understanding of the best possible design? So do you ever like remove that restriction to see where like the material would naturally flow? Like the same is done with topology optimization when you have to have your design space. If I notice that material is building up on one of the walls that I've created, I know that I can get a lighter weight, more optimal structure. If I remove that wall, it allows the material to sort of flow in that region. And so I was wondering if you ever sort of remove those first initial restrictions to observe
you can also
true optimal, if such a thing exists.
I think when you play around first with algorithms, you're pretty free from, and then when you know it will be printed, it will be a product, then you kind of add the constraints as you go. But what you mentioned again leads back to the human factor. So we cannot always assume that an algorithm by default comes up with the perfect thing if the person in front of it commands it in the wrong way. We very much need engineers to be on the higher level and say, I want to trade this aspect against this aspect. This is more important than the other one. This is how you can then direct the algorithms.
Yeah, it would be really interesting to see if you handed that aerospike engine to another engineer and let them come up with the algorithm to generate it, how different would it be?
It would be very much different.
Yeah, I'm sure.
Because I try to encode my knowledge, but another engineer might have different perceptions of how to solve a problem. So he might implement completely different cooling channels and so on. So
Yeah.
these things that you see are interpretations. So the computer is interpreting my knowledge, basically. So it's very much human dependent still.
Okay, interesting. Ladies, this is almost the end. So I would like you to share your last thoughts. How do you see these topics, this topic evolves moving forward? Do you have any key insights that you would like the audience to keep in mind at the end of this panel? I will start with Erin.
Yeah, I think that this is an extremely interesting and exciting space, because I think over the last years, metal AM technologies, and just AM in general, has progressed at an incredible rate. And all along and during that process, there's been these, simulation and design tools that are sort of running constantly, trying to keep up. And I think that we've hit the moment where, topology optimization has become more or less a standard design tool. Like all of your major CAD programs offer something, and your major simulation tools as well. And I think we're seeing the same with generative design and, new and interesting ways to approach CAD in general, like we're seeing with Hyperganic and with Topology. And so I think that when we sort of combine these new manufacturing methods and these new simulation tools and design tools, along with this changing mindset that engineers are now finally sort of catching up or taking into account, I think we're going to see really brilliant things happening in your future. So I think it's been a really fun and exciting ride, and I really look forward to what's coming next.
Thank you, Erin. Josephine, any last
Yeah,
thoughts?
I agree that with the new methods, we can actually engineer much more exciting objects. My gripe is slightly that when I go to trade shows, so I was at Rapid in the US, the 3D printed objects don't always blow me away. Like, I think there's still space. There's still more to come. And I think what's very important is that we foster the excitement for these tools in the next generation of engineers, because you don't really, right now, it's not part of the curriculum for engineering students. So
Yeah.
they are still taught and confronted with the traditional way of doing things. So we as Hyperganic try to go out to the universities and educate people about what's also possible. And
Yeah.
ideally, we make it fashionable for young engineers to become an algorithmic engineer and do things smarter and differently to how the old generation was used to doing it. Because if we want to solve stuff like climate change and come up with true innovation, new methods need to propagate through the entire field of engineering. And frankly, I think it's super exciting. So I wish more engineers would be excited about that stuff, get to work and come up with awesome objects and solve problems and so on. So I hope it catches on, as you said.
Thank you. Thank you, Josephine, and thank you, Erin. Thank you, ladies, for being part of this conversation. And to the audience, that is listening around the world, thank you for being here today during this Additive Talk session. I hope this session has been very insightful for you and useful in any projects that you're working on right now. So stay tuned for the next panel. And please keep in mind that during the month of August, we are not going to have an Additive Talk session. So the next panel will be announced soon and will be conducted only in September. So stay tuned and stay safe wherever you are in the world. Thank you again. Thanks, ladies.
Thanks. It's been
Thank
fun.
you.
Have a nice summer.
Have a nice summer, you too.
Bye.
Bye.
Bye.